This is 4.4 counting techniques. And as we alluded to a little bit earlier, if we were rolling 2 dice, it's pretty easy to write out all 36 outcomes. Well, not easy, but you could make a picture that shows all 36 outcomes, right? But if we were rolling 5 dice, there would be 7,776 different outcomes. And that would be a really big piece of paper to show all of those outcomes on it, right? And so how do we get that number? How do we know? How do we start dealing with situations where we cannot visualize all of the outcomes? There's just too many of them. And so this is where counting techniques come in. So these are techniques that we can use to be assured that we've accommodated all of the possible outcomes in a situation. And that's really what we're looking for. So let's begin with this first rule. And there are basically 3 rules. And so the first one is called the multiplication rule. And the multiplication rule for counting individual events is you just multiply those events together. You multiply the number of outcomes for each event together. So for example, if you had a t-shirt company and you produced 4 different sizes, small, medium, large, and extra large, and then you produced 3 different colors, red, blue, and green, how many different t-shirt options could you offer in total? Well, you'd say I've got 4 different sizes, and I've got 3 different colors, so 4 times 3 is 12. And if you wanted to, this one's not too bad because we actually could sort of draw this out. So you could say, okay, I've got a small red, I've got a small blue, I've got a small green, and then I've got a medium red, a medium blue, and a medium green. And then I've got a large red, a large blue, a large green, XL red, XL blue, XL green. And so you've got 4 going this way, you've got 3 going this way. These would be your sizes. If you want to organize it that way, these would be your colors, and 4 times 3 gives you 12. And so there are all 12 outcomes, piece of cake. Well, let's get a little bit more difficult, something that you can't write out, okay? And so let's say you go to your favorite restaurant where you get your choice of 1 or 3 salads, and then you pick 1 of 8 main entrees, and then you get to pick 1 of 5 desserts. And so how many total different combinations of meals could you have? Well, it would be 3 times 8 times 5, which is 120 different options. If you were to select one of those, the probability of someone selecting one would be 1 out of 120. So for example, if we talk about maybe you want to find the probability of someone selecting the chef salad with the steak as the main meal and apple pie for the dessert, that would be 1 out of 120. And where does the 120 come from? It comes from the total number of options. Now, we don't need to make a diagram or a picture or a spreadsheet to show all of these different outcomes. We could just calculate it, 3 times 8 times 5. So this is the multiplication rule. This is what we start with. And this is the foundation of everything that we do from here on out, multiplying these things together, okay? We're not adding them together, we're multiplying. Let's talk about repeats. Are you allowed to repeat items in a single event? Like, for example, these are 3 separate events. You got your salad, you got your main course, you got your dessert. What if we just did like one event and we decided whether or not you could do repeats? So let's take a look at this. So in this first scenario, we are going to allow repeats. We are going to let repeats be permitted in this situation. So let's say that you have 3 tiles, and on each tile is printed a letter, A, B, and C, okay? So you put the tiles in a bag, you shake it up, and you pull the letter out, okay? You get the letter B. Then what you do is you take that tile and you put it back into the bag. This is important. You don't leave it out. You put it back into the bag, you shake it up. So now again, there's 3 tiles back into the bag and you pull one out. This is allowing repeats. You are allowed to pick the same thing multiple times. So in this situation, if you are picking out, let's say you've got 3 trials, the ways that you can pick the first letter, there are 3 ways, A, B, C. So you could pick an A, you could pick a B, or you could pick a C. You put the tile back in, you shake up the bag, and for the second letter, again, there are 3 ways, A, B, and C. And then you put that tile back, you shake it up, and you draw a third letter, and you get A, B, or C. So it's 3 to the third. Now where does the 3 come from? There's a couple 3's here. So this 3, this base, this comes from the number of outcomes. So there are 3 outcomes. So we'll say outcomes. These are the number of outcomes that you have, the number of choices that you have for each draw. This 3, the exponent, comes from the number of trials that you are performing. So we are drawing 3 trials. So we did a quick calculation a little bit earlier talking about dice rolls. If you wanted to find, if you're rolling 2 dice, it would be 6 to the second power. This is the number of trials. You are rolling 2 dice. So you're doing 2 trials. And the 6 is the number of outcomes. There are 6 sides to the dice. So if you roll a 6-sided dice and you have 2 of them, there are going to be 6 to the second power, which is 36 total outcomes. If we instead change that to 5 trials, like in Yahtzee, you've got 5 dice, each is 6-sided, this would become 6 to the 5th power, because now you're rolling 5 trials, not just 2 trials. And this is the 7,776 different outcomes, right? 6 to the 5th power. And notice that we're using the multiplication principle, right? If you wanted to, you could write this out and say, okay, so for the first dice, there are 6 options. For the second dice, there are 6 options. For the third dice, there's 6 options. For the fourth dice, there's 6 options. And for the 5th dice, there's 6 options. 6 times 6 times 6, oh, that's 6 to the 5th power. So this is using the multiplication rule when repeats are allowed. Now let's talk about what happens when repeats are not allowed. And so if you go back to our bag with the 3 tiles, the A, B, and C, let's say that you draw out something from the first. So the first draw that you have, there are 3 tiles that you can select from. You can pick A, B, or C. So you pick one out. You do not replace it. You do not put it back in the bag. That tile stays out of the pool that you can select from for the second letter. And now instead of 3 tiles, there are only 2 tiles. And once you pull that tile out, you do not put it back into the pool. It stays out. And then there's only 1 left for your third option. So using the multiplication principle, this is 3 times 2 times 1, which is 6 options. And look what happened. We went from 27 total options with repeats down to 6 options without repeats. Huge difference in the number of outcomes. So let's say instead of 3 tiles, let's say you got 15 tiles. Okay, so the letter's 15. I think that goes through O, maybe. A through O are 15. And so if you have 15 items and you're picking them out, if you allow repeats, then it's 15 times 15 times 15 times 15. How many times? 15 times. And so there are 15 to the 15th power possible outcomes. And there it is right there, a lot. If you do not allow repeats, if repeats are not allowed, then every time you draw a letter, you do not put it back and it reduces the pool by 1. So you have 15 and then 14 and then 13, then 12, then all the way down to 1 item. And this is the number of outcomes that you have. So how are we going to calculate this? How are we going to do this? I'm going to type 15 and then X to the Y 15 equals. And there you go. That's how many ways, if you had 15 letters and you allowed repeats, that's how many different ways you could do it. What about this 15 times 14? Okay, hold on. We'll do this math. So we'll say 15 times 14 times 13. Are we there yet? Are we there yet? No, not yet. Are we there yet? No, hold on. Are we there yet? Quiet from the back seat. You kids, if I hear you say that one more time, I'm turning this car around. Okay, there we go. So we just calculated the whole entire thing. But boy, that was a pain to calculate. And this was just for 15 items. What if I had 100 items? Do you really expect me to do 100 times 99 times 98 times 97? No. So what mathematicians did is they created a specific function that does this calculation. It calculates the first item multiplied by each item subsequent to it, -1, all the way down to 1. And this function is called factorial. And it has a little exclamation point at the end. And so 5 factorial is 5 times 4 times 3 times 2 times 1. And then it does the calculation for you. 8 factorial is 8, 7, 6, 5, 4, 3, 2, 1. And so if we go back up here, we could just type 15, and then right here is the factorial button above the number 9. So n with an exclamation point. And if you hit that button, ta-da, now you get the exact same number. And it's a one-click operation. You don't have to type 15 times 14 times 13 times 12. You just hit that factorial key. I want to show you the spreadsheet for 4.4. And so here's the spreadsheet, and there is a function if you want to do the factorial, just to show you off to the side, it's FACT. So if you want to find 15 factorial, you just type equals FACT and then the number in parentheses, and there is 15 factorial. Don't use the exclamation point. If you try to put in the exclamation point, 15 factorial, it's going to give you an error. It's going to say, I don't know what you're talking about there. What is this exclamation point? Why are you putting text in with numbers? I don't understand this. That's what the spreadsheet's saying. And so use the formula FACT and then put the number in. Sometimes it's difficult for students to see all of the different options. And so in this spreadsheet, we could say I've got a coffee shop and I offer 2 types of coffee, hot and iced. And then I offer 2 types of milk, whole and skim. And I offer 2 types of flavoring, pumpkin spice and caramel. And you can see that I have 2 coffee options, 2 milk options, 2 flavor options, and 2 times 2 times 2 is 8 different types of coffee. So I could advertise, hey, come to the coffee shop because we offer 8 different options for coffee. And if you don't believe that there's 8, you can actually see them all right here. And so there's a code up here that will actually take each one of these and create the entire sample space. So here is the hot coffee made with skim milk and caramel flavoring. And here is the iced coffee with skim milk and pumpkin spice flavoring. Now, here's the cool thing. We can add things to each one of these lists, up to 10 items, and the sample space will automatically be generated. I need to offer another type of coffee. So I have a hot coffee, I have an iced coffee. What other type of coffee can I offer? Go ahead and type it in the chat. So let's do a blended coffee. As I type blended, it automatically added that to my list. Let's go to milk. So I need, give me 2 types of milk. I've got whole milk, I've got skim milk. Give me 2 additional types of milk. 2%, I'm gonna write it 2% milk and soy. Okay, we'll do 3, soy milk and oat milk. So now notice as I add these, as I add the 2%, the soy and the oat, my milk options go up to 5 options, and look at all of the different types of coffees I can offer now. Now I can offer a blended soy pumpkin spice. Okay, now let's do the last one. Flavors. I've got pumpkin spice, I've got caramel. What other flavors do I need to add to my coffee? Mocha, vanilla, amaretto. Oh, no one has said amaretto in any class ever. That is awesome. I forgot about amaretto. Yeah, that's a good flavor. Any others? 1, 2, 3, 4, 5. I've got 5. We'll do 2 more. You got 2 more? Hazelnut, almond. There we go. Okay, so now I have, you'll notice over to the side here, column E and F. I now have 3 coffee options, 5 milk options, 7 flavor options for a total of, drum roll please, 3 times 5 times 7, 105 different types of coffee that you could order. And if you don't really think that there's, oh, come on, it's not 105, is it really? Yep, look at the sample space. Here they all are. Iced coffee made with skim milk and hazelnut flavoring. That's one of the 105. Here's the blended 2% hazelnut coffee, or the, let's do the iced oat milk vanilla flavored coffee. Oh, that sounds good. Now we do the exact same thing with the letters. So if you go to the letter, you can see here are the letters you can pick from. And then the sample space is distributed here, but you're going to notice some interesting highlighting. And this has to do with whether or not you allow repeats. So if repeats are allowed, AAA, you can have 3 times 3 times 3, which is 27 different options. If you do not allow repeats, so that means AAA is not allowed. You can't have it because there's 2 A's. And ABB is not allowed because there's 2 B's. You can only allow situations where there are no repeats. That's what the red highlighted cells are. These are a restricted sample space where we do not allow repeats. So there are 1, 2, 3, 4, 5, 6 options where letters are not repeated. And if you don't believe it, you can actually look at the sample space and count them, right? This one, any repeats? Yep, it's out. Repeats? Yep, it's out. Out, out, out. There you go. There's the first situation where you do not have a repeated letter. Then go to the next one. Oh, A's are repeated. That's out. Here's the next situation where you don't have a repeated letter. And you can see that there are 3 times 2 times 1, 6 different options. Now let's talk about order, or sometimes this is also referred to as sequence. And we have 2 situations. One situation is where sequence matters or order matters, and the other one is where it doesn't matter. And let's go through and explain these. So the first one we're going to look at is a situation where order matters. The sequence of the numbers matter. So think about maybe your cell phone. And on your cell phone, maybe you have an unlock code. And so you've selected the numbers 1, 2, 5, 8 as your unlock code. So you pick up your phone, you type in 1, 2, 5, 8, and boop, it unlocks, right? Is that the same code? Is it the same code? Is 8, 5, 2, 1. So if someone picks up your phone and they type in 8, 5, 2, 1, does it unlock? And the answer, of course, is no. Why doesn't it unlock? They have the exact same 4 outcomes. They have a 1, they have a 2, they have a 5, they have an 8. But in this case, not only do they need the correct 4 numbers, they need them in the correct sequence. So order matters. You would count this as one code, and this would be a second code. They are 2 different codes. And so you would say that these 2 are not equal. They are not equal. They are not the same code. 1, 2, 5, 8 is different from 8, 5, 2, 1. Order matters. And this is called a permutation. Think of it like a PIN number. Permutation, PIN number. When you unlock your phone with a PIN number, or when you go to an ATM and have to enter your PIN number, the order matters. So how do we calculate how many different ways you could do something? Well, here is the formula for a permutation. So if you have 5 objects, let's say I'm asking you to create a 3-digit code from 5 numbers. So I'm going to give you the numbers 0, 1, 2, 3, 4. Okay, there are 5 numbers here. And I would like you to take those 5 numbers and create a 3-digit code. How many different codes could you create? Let's start out with 0, 0, 0. What about 0, 0, 1? What about 002, 003? How many different ways could you do this? And so what we're going to do is we're going to do this calculation. You take the total number of objects, that's n, and you put that right here. And then you take the number of that pool that you want to select, and that is r. And that is r. So if we have 5 numbers and we want to select 3 of them, and the sequence matters, this is the formula. So it's going to be 5 factorial. So you're going to take 5 factorial, and you're going to divide it by 5 minus 3 factorial. Just as a note, you cannot distribute this factorial inside of here. Okay, so 5 minus 3 factorial is not equal to 5 factorial minus 3 factorial. You cannot do that. Bad. Do not try to play that game. First, subtract the 5 and 3, and then raise that to a factorial. Okay, so it's 2 factorial. 5 minus 3 is the 2, and you get 2 factorial. So once you have this, you'll notice that these numbers cancel out and you get 5 times 4 times 3, which is 60. So there are 60 different ways, 60 different outcomes from taking 5 objects and picking 3 of them if the sequence matters. What if the order doesn't matter? You don't care about the order of the things. This is called a combination. And here's an example of a combination. Okay, so let's say you go to your favorite pizza place and you order anchovies, bacon, and cheese. Get it? ABC, anchovies, bacon, and cheese. Is that the same? If you order a pizza with anchovies, bacon, and cheese, is that the same pizza as a cheese, bacon, and anchovy pizza? Is it the same? Yeah, it's the same pizza. You imagine going to a pizza place and saying, I'd like an anchovy, bacon, and cheese pizza. And, they take your order and they go back, they make the pizza and they bring it out to you. And you're like, oh no, this is not the pizza I ordered. I ordered anchovies, bacon, and cheese. And you gave me cheese, bacon, and anchovies. I'm sorry, we don't have the right pizza here. Of course not, right? Like they kick you out of the pizza shop for doing that. These are the same pizza. And the way I remember combinations is combination pizza. If you go to the frozen food section of your local supermarket, you will find combination pizzas. That's what they call them, combination pizzas. And so that helps me remember, oh, combination pizza, order doesn't matter. When you order a pizza, it doesn't matter the sequence of the toppings that you select. You can order anchovy, bacon, and cheese, or you could say cheese, bacon, and anchovies, and you're going to get the same pizza. So this pizza, anchovy, bacon, and cheese, is the same as this pizza. They count as one. As a matter of fact, anything with 1A, 1B, and 1C is the same pizza. And we could list them if we really wanted to. ABC, right? ACB, BAC, BCA, CAB, CBA. Here are 6 pizzas with the same 3 ingredients listed in different sequences, and they all count as one pizza. Now, if this was a permutation, you would have 1, 2, 3, 4, 5, 6 different sequences, right? If order matters, you would have 6 different sequences. If order doesn't matter, those 6 now count as one sequence. So we should have far fewer unique sequences with a combination. Here is the formula for the combination. And notice it's the same players. You have n total objects, right? Total toppings of pizza to pick from. And you are going to pick R of those total objects. So it's NCR. You may also notice that built into this formula right here, that is NPR. The permutation formula is actually part of the combination formula. You just divide by one additional factorial. You divide by R factorial an additional time. See that? So 3 factorial is the only difference. Right here is the permutation. Right there is the permutation. And then you divide by 3 factorial and you get combination. So you can kind of remember this by, memorizing that permutation formula. And so if you do the calculations on this, you get 5 factorial divided by 2 factorial, 3 factorial. All these things cancel out and you end up with 10 options. And so we go through and we look at a few examples of this. So let's say that you are a member of a club. Maybe there's a student senate club on West Shore's campus, and there are 15 people that are members of this club, and you need to pick 3 officers: a president, vice president, and secretary treasurer. So the first question is, does order matter? If you select Abe, Ben, and Carol, is that different than if you selected Carol, Abe, and Ben? Yeah, those are different situations. In the red situation, Abe is the president. In the green situation, Carol is the president. So these are different things. So order really matters. It matters who you elect first. So that means this is a permutation. Order matters. It's a pin number. The sequence matters. And so you're going to plug in 15 for n. That's the total number of objects. And you need to pick 3. So it's 15 factorial divided by 15 minus 3, which is 12 factorial. So 15 factorial over 12 factorial. All of these things cancel out. 12 is gone. 11 is gone. 3, 2, 1 are gone. And you end up with this many different options. All right, let's look at another situation. So now let's say you have a class of 20 students and we want to create some groups. And so we want to pick 7 students to be part of a group. So how many different ways can we do this? And again, the question is, does order matter? So if I pick this group, student 1, 2, so I give everybody a number. I pick student 1, 2, 3, 4, 5, 6, 7. Is that the same group as 7, 6, 5, 4, 3, 2, 1? Yes, they are the same group. Notice in the presidential, vice president, and secretary, there was almost like a sub-organization. Like we're picking 3 people, but then those 3 people are going to be sub-organized into president, vice president, secretary, treasurer. Where in this situation with the group, we're just doing 7 people, right? Pick 7 people. And so this is the situation that we have. Because order doesn't matter, this is a combination. So we're going to use the combination formula. So 20 is the pool of people that you're selecting from, the number of students. 7 is the size of the group. And so you use the combination formula to get 77,520 different ways that we could select 7 people out of 20 to form a group. So here's the last tab of the spreadsheet. And you can see what I have here are the total number of items and the number of items to select. So if we allow repeats, if repeats are allowed, remember that was just the exponential rule. So we're going to say this equals, so we've got n options raised to the power of the number of events. So n to the 4th power, or 9 to the 4th power, sorry. So that's how many different ways you could select 4 objects from 9 if repeats are allowed. You've got 9 objects, so 9, 9, 9, 9, 9, 4 times. Okay. What if repeats are not allowed? And we have 2 ways of doing this. Let's start with a permutation, and then we'll do the combination. So if repeats are not allowed and order matters, you have a permutation, right? This is a pin number. 1, 2, 3, 4 is different than 4, 3, 2, 1. In this formula, you'll see that we have exclamation points, and you can't use an exclamation point in this formula. So if you type 6 with an exclamation point, it thinks that it's a text. And if you say, okay, it's not text, this is something mathy, so I'm going to put an equals inside, it's going to give you an error. The spreadsheet doesn't understand the exclamation point means factorial. The spreadsheet has a function for factorial called FACT. So if you want to find 6 factorial, you have to type equals FACT and then the number 6. And that will calculate 6 times 5 times 4 times 3 times 2 times 1. So what we would like to do is we're going to build a formula in this green region that models what we're doing here up top. Okay, so we're going to model this. So we're going to say equals, I need n factorial. So I'm going to say FACT, and then I'm going to select n. I'm going to divide that by FACT of n minus r. And there is the step-by-step calculation using factorials of 9 objects in a pool, and I need to pick 4 of them. Repeats are not allowed. Order matters for a permutation. Now, this is a lot to enter. This formula right here is a lot to enter. So spreadsheets made it simple, and they actually gave you a formula. Equals PERMUT. That's the formula. You select n, comma, r. Now, in the formula, you'll notice it says k. So they use a different formula, a different variable for the number of items that you're selecting out of the pool. But we use r for the textbook. And so we're just going to put that right in there. And you'll see we get the exact same number. So here's how we calculated it by hand. Here's how we calculated it using the shortcut formula in Google Sheets. Okay, we'll do the same thing for combinations. So how many combinations can you have? And so we'll do the exact same thing. We'll build it step by step by hand. So we'll say FACT of n There we go. This is the factorial then. And then we're going to divide this by, and I need to use two sets of parentheses. So I'm going to say FACT of n minus r. And then I need to multiply that by FACT of r. It does not like the square brackets. You got to use parentheses. Okay. So there we go. We'll put those parentheses in there. And there we get that. Or you could bypass that whole mess and just type equal COMBIN for combination n comma r. Okay. And you see we get the exact same number. And so let's say that you had 26 letters of the alphabet, 26 letters, and you need to create a license plate that has 6 items in it. So how many different license plates could you create? Well, if you allow repeats, A, there are this many license plates you could create. Enough for everyone in the state of Michigan by far, enough for everyone almost enough for the entire country. So if you had 26 letters, you had to pick 6 letters, and you would allowed repeats, you could have this many. If you don't allow repeats and order matters, A, B, C, D, E, F is different than F, E, D, C, B, A, then you can make this many license plates. And on the other hand, and that would be the situation you'd have because those are different license plates. If on the other hand, you say, okay, A, B, C, D, E, F is the same license plate as F, E, D, C, B, A, or another way to say this would be if you had 12 toppings on a pizza and you had to pick 2, how many different pizzas could you order? 66 different pizzas.